In advance tonight, someone wanted to go over kilojoules per mole. It was from the Unit 6 FRQ, and there was a lot of confusion there, and a lot of people just not so sure what was going on. So, I'm just going to make up a reaction here. It doesn't really matter who. I'm going to go over it in both perspectives in terms of solving for it and what it looks like when it's given to you. So let's say you had a reaction, it doesn't really matter what it is. 3C plus 4D. And it tells you the delta H of reaction is, or maybe it'll just say delta H. It'll say kilojoules per mole, and then there'll be a little subscript next to mole that'll say reaction. Something like that. And let's say it's negative 1,000. All right, so I'm just going to get that set up. I'm going to wait a couple minutes. I just wanted to set that up before I get started. And then I'm going to give it a one more minute just to make sure everyone's here. And I will go over it. Okay, so what this means is that as long as we have the mole ratios seen in the given chemical reaction, this reaction will release, because negative delta H means it's exothermic. So this reaction, when it occurs, will release 1,000 kilojoules, period. So kilojoule per mole reaction means as long as we have the ratios seen in the balanced equation, we react 1 mole of A with 2 moles of B, it goes to completion, we get 3 moles of C and 4 moles of D, then you'll release 1,000 kilojoules of heat. So that mole reaction part, all that means is the amount of heat that's released given the ratios. If we are given a limiting reactant, then that delta H will change proportionally to whatever the limiting reactant is. So that per mole reaction, all that means is that delta H is proportional to moles. And whatever substance is limiting is going to cause the delta H to decrease proportionally to how much it was limited by. So in the practice problems in Unit 6, you did a Q equals MCAT scenario. There's actually 2 examples of this. One of them was with a solution. So one of them you were mixing HCl with Mg, which created a solution, and which means that Mg is not going to be releasing any heat unless it's reacting with HCl. So you have to include the whole mass of them combined, because both of them were important and both of them were involved in the reaction. A lot of times you'll see these where we mix like a metal with water, and we're only concerned with the water because the heat from the metal is going into the water. So we just assume the Q in equals the Q out, and we only do the Q for the water. The reason we had to include both of them here is that this was a chemical reaction, and no heat is going to be absorbed or released unless they chemically combined based on the net ionic equation that was given to you, which looked something like this. H2. Okay? So you combine these two masses, like 100.5 grams, and you solve for Q, and Q is similar to delta H, but what Q is doing is ignoring moles, and it's just about mass. So when you get Q, your answer is going to be in joules. So don't forget your units. If you don't include your units and you just put 500, you're probably not going to get any credit. So Include your units. And then a lot of times the next question is going to be, what's the delta H in kJ per mole? And again, just focus on the units here. That is telling you I want a final answer that is kilojoules in the numerator and mole in the denominator. So it's literally telling you to divide your answer in kilojoules by your answer in moles. So in this case, typically you just take your joules and you divide it by 1,000, and that's just a quick conversion to kJs, and then that's done. And then the moles you'll get from your limiting reactant, right? And in this case, the example I haven't been doing is magnesium oxide, actually. And you did like the 0.5 grams, and it weighed like 40.3 grams per mole. Grams go away, and you're left with whatever that is. I don't know, 0.0 something, 0.02. I don't know. So you get X moles, whatever that is. And then now you take your answer in kilojoules, divide it by X, and then you'll get your answer in units, kilojoules per mole. So it's basically asking you to identify your limiting reactant, because as we discussed earlier, whoever your limiting reactant is, delta H is proportional to moles. The amount of heat this made-up reaction is releasing only happens if we have a mole of A and 2 moles of B. If we have 1 mole of B and excess A, we would predict that this would release 500 kilojoules because it's half the amount of moles. So delta H is proportional to moles. When you do Q equals MC delta T, you're getting joules, which is just representative of heat and is kind of independent of moles of the reaction. It's just saying this is how much heat we're releasing. Kilojoules per mole is taking into account the limiting reactant and is telling you that reaction as a whole, not just saying like, what is this like Q equals MC delta T doing? We are getting the delta H for this whole reaction. So if we converted it up to 1 mole, you might be able to, so you would be able to do like a percent error. So you calculated the delta H in kilojoules per mole to be whatever. Now you can compare it to the actual delta H in kilojoules per mole. Why was yours calculated to be smaller? Oh, heat was lost to the surroundings. So the delta T in my Q equals MC delta T, that's pretty much the only variable there, right? Chances are you didn't like drop magnesium on the ground and then break it in half. C is a known constant. Your delta T would be smaller because you're losing heat to the environment. Therefore, your calculated delta H would be smaller in magnitude, leading to a percent error. But that's the basics of kilojoules per mole. It's just taking your answer in joules, converting it to kilojoules by dividing it by 1,000, and then dividing it by your moles of your limiting reactant, and then that's it. You get a number, and those units are kilojoules over moles. Any other questions? Another thing while you guys are like contemplating that I saw popping up is we're confusing K versus K. So there's little k, which is involved in rate. That's the rate law constant. So that's like rate equals k. And in this scenario, when you're setting up your rate law, the only thing you should be plugging after this are reactants, and you'll typically get it from a data table. But if you have like those elementary steps, so it's like step 1 is A plus B makes C, and this is your slow step. And then 2 was C makes D, and this was fast. Remember, if the slow step is the first step, then the first step is the rate determining step. The first step helps you determine your rate law directly. You would say rate equals K A times B. So little k is your rate law constant. Your rate law constant applies to kinetics. It applies to how fast are my reactants turning into products. So I'm only concerned with reactants. What is the conversion of these reactants turning into products? That's little k. Big K can be like Kc, which is K in terms of concentration. You can be Kp, which is K in terms of pressure, regardless, or we've done Ksp, which is K in terms of solubility. Regardless of what it is, regardless of what the big K is, we're talking about equilibrium. We only include gases and aqueous substances, so no solids, no liquids. Those are pure substances. Those are substances that we don't measure in terms of concentration. Those are substances that are not really affected by pressure. Those are substances that are not dissolving. They split into ions, which is the ones we're concerned with Ksp. And that is when you take all the products and you raise them to the power of their coefficients divided by the reactants raised to the power of their coefficients. Okay? So that's big K. Big K is equilibrium. Big K is when the reaction is reversible. Big K will be given to you in some way, shape, or form. And it will be unitless. So that's a big indicator. It's equilibrium, it's reversible, it's unitless, and when it's really big, like it was really big in that one practice problem we did with EDTA, then we assume it goes to completion. We assume that entire thing is reacting to completion. And it'll hint you towards that in the question. It said, based on the K value, what can we assume the concentration of barium to be? And it was trying to tell you, please don't set up an ice table. Please don't use the quadratic equation. Please don't waste time. Big K goes to completion. Dunzo. Little k in this rate law has units. So if you solve for the rate law constant and you don't give me any units, you're going to get it wrong. Or at least get half credit, because it will always probably ask you for units, and we always stress that you need units. Please don't forget your units. So, final little thing, when you're doing the rate, remember rate is always in molarity per second. You're doing K, and then you're multiplying it by things that are just pure molarity. Everything on this equation, when you have rate equals K times concentration of substance times another concentration may be squared. Everything on the right-hand side is molarity. Everything on the left-hand side, which is one thing, is molarity per second. So, or I should say molarity per time, because that was another thing I noticed. Some of you were given something in minutes, and then you just said, nope, it's in seconds. You're going to get it wrong if you just change the unit to whatever fits, some problem you did the day before. So let's change this so we eliminate confusion. It's molarity per time. So you'll notice all I have over here is molarity. All I have over there is molarity. My final answer for K is going to be something over time, no matter what. If you divide rate by one molarity, like there's just one substance on the right-hand side, it's a clear first order reaction, the molarities cancel out, and your K is just 1 over time. If I have two substances on the right-hand side of the equation, then one of the molarities cancel out, the other one does not cancel out, and your K will be 1 over molarity times time. If there's three substances on the right-hand side, or there's one substance and the second substance is second order, then it's 1 over molarity squared time, etc., etc., etc. You'll notice on the practice problems, they might have it as like mole liter -1, and then you might get confused. What is mole liter? Oh wait, liter to the -1 power. That just means put it in the denominator. That is molarity, because moles over liters is molarity. You can just rearrange it so that it becomes molarity. So you're just dealing with canceling out M's, because molarity is moles per liter. So don't worry about that. That's fine. That's fine. You can totally convert it to molarity. Not really converting it, it's just like making it equal to what it is. And then it'll be a bit easier in terms of canceling things out. All right, I didn't get any questions, so I'm donezo. I'll see you later.